Hello everyone and welcome to this memory map. Today we're discussing the chapter on capacitors. Now capacitors make up a very important part of electronic circuits. Some of the main uses of capacitors are medical, for example in a pacemaker, or completely electronic, like for example in our telephones, that is our mobile phones, and in our computers. So let's begin studying capacitors. The first concept in understanding capacitors is that of the dielectric. So what exactly are dielectrics? Dielectrics are non-conducting substances that have a negligible number of charge carriers. The exact opposite of this is a conductor. A conductor has a large number of carriers, that is charge carriers, and it is a conducting substance by definition. So I want to take this time out and explain what is the real difference between a dielectric and a conductor and why that matters in case of capacitance. So let me give you an example. Whenever you have a conductor, you know that there are carriers in a conductor which are both positive as well as negative. And as you can see, they are free to move around. And if you place this conductor in an external electric field, there will be movement of these charges. And now obviously the positive charge moves in the direction of the electric field and the negative charge moves opposite to it. So you can see that there is a separation of charges which is brought about by the external electric field. And this is obvious. We know that charges are affected by electric field. But how is it so important in a conductor? It is important because in a conductor, the charges are actually free to move. And therefore, when you apply an electric field, the charges move. There is a separation of charge, and therefore you get this new charge distribution. Now, what is the importance or significance of this charge distribution? Because there is this separation of charge inside a conductor, what happens is that an induced electric field is set up inside the conductor. And this induced electric field is exactly opposite to the external electric field which is acting on the conductor. And again, why is this important? Because in electrostatics we learned that the field inside a conductor is zero. And now what I'm doing is explaining to you why it is zero. It is zero because of this opposite induced electric field that we can see in the picture. Now this opposite induced electric field is exactly equal to the external electric field, and because it is opposite, it cancels the external electric field inside the conductor, and therefore the total field inside a conductor becomes zero. And this is how a conductor actually makes sure that there is no field inside, by giving back an induced opposite field. Now, this is an important point of difference between a conductor and a dielectric. Let's see what happens if I place a dielectric in an external electric field. First of all, like we said, a dielectric has negligible number of charge carriers. Also, the movement, that is the free movement of charges in a dielectric-like substance is not possible. However, we know that charges are affected by the electric field, but since they cannot move, what will be the effect of the electric field on the charges? The effect will be that the electric field will make them either stretch or align. So we'll see quickly in some time what I mean by stretching or aligning. But basically what I'm trying to say is that if a dielectric is placed in an external electric field, then there will be some sort of separation of charges just like there was in the conductor, but this separation will not be very prominent. And because of this separation, that is either it will stretch or it will align, because of this there will still be an induced electric field which will be set up inside the dielectric, and this induced field will still again be opposite to the external field. However, in the case of a dielectric, the induced electric field, which is EI, will not be big enough to cancel the external electric field, and therefore in this case we say the opposing field, the opposing induced field EI, does not exactly cancel the external field, it only reduces it. And therefore in this case we say that E is actually greater than EI, and therefore it will not cancel each other, and therefore the field inside a conductor is reduced, as you can see, but it is not zero. So this, you can see, is the major difference between a dielectric and a conductor. Now, the next question is, who decides how much it will be reduced? Will it become half? Will it become 1/4? The extent of this effect, that is how much it will reduce, will depend on the material of the dielectric. So there are many types of dielectric, And so next thing we want to understand is what is the material of the dielectric. Now in general, dielectrics are of two types. They are made up of either polar molecules or non-polar molecules. So first let's take a look at the non-polar molecule. A non-polar molecule is one in which the center of the positive and the negative charge coincides, which means that the positive charge center and the negative charge center is at the same place. This results in the fact that, which means that when there is no external field, when there is no other external field, the molecule itself does not have any dipole moment. That means there is no intrinsic. Intrinsic means there from before. There's no intrinsic or permanent dipole moment of the molecule. Why? Because the centers are coinciding. And if the positive and the negative charge are at the same place and there's no distance between them, so how can you make a dipole? You cannot. So there is no dipole moment in such a molecule. And an example of this would be the carbon dioxide molecule or the hydrogen molecule. And you can see that usually a non-polar molecule has some kind of symmetry. For example, here the carbon dioxide molecule is symmetric about the y-axis. The positive charge center, that is the red ball center, and the negative charge center of that is the yellow balls are the negative charges, their center is also lying on the same axis, and the positive charge center also lies on the same axis, and they're symmetric about the y-axis, as you can see. The same thing happens with hydrogen. In case of hydrogen, both of them are exactly the same molecule, so their positive and negative charges will obviously be at the exact center of the molecule, and like I've already said, it is symmetric. So look for symmetry, and usually that will be a non-polar molecule. On the other hand, then, a polar molecule is one in which there is some separation between the positive and the negative charges, even when there is no external field. So that means that even when there is no external field, there will be some distance between the positive center and the negative center. And if there's a distance, that means that it has a permanent dipole moment. There's always a dipole moment present because naturally only their centers are not colliding. The positive and negative charge centers are not colliding. So let's take an example of a polar molecule. Here I have the hydrogen chloride molecule. Here, as you can clearly see, the positive end of the molecule is on the yellow side and the negative end of the molecule is on the red side. So they are clearly separated. Similarly, we can see this in the water molecule, which is also a polar molecule. You can clearly see that the positive end, that is the yellow spheres, are to one side, and the negative end, that is the red spheres, are to the other side. So again, here there is a clear separation of the positive and negative centers. Also remember that, like we said, you can also check that polar molecules will usually not have any symmetry. So here you can see that they are not symmetric above the y-axis. Neither is the HCl molecule, neither is the H2O molecule. And this is a sort of good guess to check if a molecule is polar or non-polar. So we saw that when dielectrics are placed in an external electric field, the electric field affects the dielectric, and there will be either something called a stretching or there will be alignment. So now I want to see in which case will there be stretching and in which case there will be alignment, and what exactly do these mean. First, we'll take a look at non-polar molecules in an electric field. In an external electric field, the positive and negative charges of a non-polar molecule are displaced in opposite direction. So remember, we said that non-polar molecules are those in which, in the absence of external electric field, that is, if there is no external electric field, inside the molecule the positive and negative charge centers are exactly at the same place, and we said that this means there is no natural dipole moment to a non-polar molecule. However, when you place it in an external electric field, the non-polar molecule, whose plus and minus centers were exactly coinciding, as you can see, this will actually be displaced in the opposite direction. So when you place it in an external electric field, these centers will be separated from each other, and this is what we call as stretching. So non-polar molecules undergo stretching in an external electric field. Now you can see that stretching has occurred in these non-polar molecules, and because of this we have induced dipole moments. Why do we call it induced? Because naturally these molecules did not have any dipole moment. Now, because they are placed in the external electric field, there is an induced dipole moment in each of these molecules. And therefore, we say that the dielectric is polarized by the external field. Why polarized? Because the polarities, that is the positive and the negative centers of the molecules, have changed, that is separated. So it has been polarized by the external electric field. Now, all the dielectrics that we will be studying in this chapter are what are known as linear and isotropic dielectrics. So, we call them linear isotropic dielectrics. What does this mean? These dielectrics, they satisfy two conditions. The first one is that the induced dipole moment is always in the direction of the external field, and second is that the polarization is directly proportional to the strength of the electric field, which means the greater the electric field strength, the greater will be the polarization. That is, there's a linear relationship between the polarization and the electric field strength. So these two conditions are satisfied by linear isotropic dielectrics, and these are the ones that we are studying in this chapter. So we are only going to deal with linear isotropic dielectrics. Okay. Finally, we say that all these induced dipole moments of all the molecules will all add up to give me a net of final dipole moment of the dielectric in the presence of the external field, and this dipole moment will be in the direction of the external field. Now, once you've understood that, let's see what happens when you remove the external electric field. If you remove the external electric field, then because of thermal agitation, that is because these molecules are constantly absorbing heat energy from the outside, and because they have some thermal agitation, what will happen is slowly they will go back to their original position, and therefore the dipole moment will be lost, and therefore we say that it was an induced dipole moment because it's only there when there is an external electric field. So this dipole moment will go back to its original position, and there will be no induced dipole moment. It will go back to zero. Let's see what happens in the case of a polar molecule. In case of a polar molecule, as you can see in the figure, the molecules already have centers which are separated from each other. In each and every molecule, the positive and the negative part of the molecule are separate from each other. They are already separate. So you can see that even naturally, without any external electric field, a polar molecule has a dipole moment. So each individual polar molecule has a dipole moment even in the absence of an external field. But in the absence of the field, all of them are in random directions, and therefore overall the material does not have a net dipole moment. So now we come to ask the question, what happens if you place these polar molecules in an external electric field? What will happen? The second type of effect of dielectrics, that is alignment. And therefore we say that when an external field is applied, the individual dipole moments all tend to align with the electric field. So they will all move in the direction of the electric field and get themselves aligned in such a way that they have to travel the least angle. It will turn through the smaller angle to align itself with the electric field. So this is the alignment effect of the electric field on the polar molecules. So now as you can see, there will again be a total dipole moment, but this is not an induced dipole moment. Why? Because it always had a dipole moment, but because there was no electric field, they were all in random directions, and overall the net dipole moment was coming out to be zero. All the electric field did was direct all the dipole moments in one direction. And when you add all these dipole moments, you get a net dipole moment in the direction of the external field. And again, as usual, we say that the dielectric is polarized. So you can see that there is a different kind of effect that the external electric field has on a polar dielectric and a non-polar dielectric. Finally, the question is, what does the extent of polarization depend upon? The extent of polarization depends on two factors. First one is the dipole potential energy in the external field, which tends to align the dipoles, and second is the thermal energy, which tends to disrupt the alignment. Like I've already said, if you remove the external field, the thermal energy or the thermal agitation will cause these to lose their polarization, and they will again all get randomly oriented, and again the net dipole moment will go to zero, but the individual dipole moment will always remain because these are polar molecules. So this is the difference between the polarization in a polar dielectric and a non-polar dielectric. Finally, from here now we can define what is known as polarization. Polarization is nothing but the dipole moment per unit volume, and therefore this is denoted by capital P for polarization. I told you the only ones that we are talking about in this chapter are linear isotropic dielectrics, and for them we have the equation P is equal to chi E. So here, like I said, we call it linear because the relationship between polarization and electric field strength is linear. So here P is the polarization, E, of course, is the electric field strength, and chi is known as the electric susceptibility of the dielectric medium. P will give us how much polarization can occur inside a material. Chi, of course, will depend on the material. So what is the effect of this polarization and what is its significance? We saw that when dielectrics are placed in an external electric field, there will be an induced electric field set up inside the dielectric. And this induced electric field will be opposite to the external field. So I want to explain this in terms of polarization. Now, the first thing I want you to remember is that the electric field will either affect the dielectric either by stretching it or by aligning it. For example, if I had non-polar molecules in an external electric field, then they would undergo stretching as we have seen. But the important point to notice is that if I take any volume, any small part volume of this entire dielectric and take a look at it closely, I will see that it has no net charge. The amount of positive charge and the amount of negative charge is exactly equal, and therefore no volume element of this entire dielectric, no matter which part you take, will have a net charge. However, of course, there will be a net dipole moment, that is the induced dipole moment in case of a non-polar molecule. So yes, there is a net dipole moment, but there is no net charge. How is it possible that when there is a separation of positive and negative charges, there is still no net charge in any portion of the dielectric? And the answer to this is the fact that the positive and negative charge centers of the molecules lie very close to each other inside the dielectric. So what do I mean by this? I mean that the effect of the positive charge centers is neutralized by the effect of the negative charge centers inside the dielectric. So as you can see, inside the dielectric, they lie very close to each other and neutralize each other's effects. However, the only place where unbalanced charges remain are the place at the surface which is normal to the electric field. So the surfaces of the dielectric which lie normal to the electric field, these two surfaces only will have unbalanced charges. As you can see, the unbalanced positive charges remain on the right and the unbalanced negative charges remain on the left. Nothing is there to neutralize or balance these charges. So the entire effect of the polarization is reduced to only this situation where the positive charges are on the right surface and the negative charges are on the left surface. And therefore we say that this entire dielectric is giving rise to an induced electric field, which you can see is the direction from the positive charge to the negative charge. This is the induced electric field EI, which is opposite to the external electric field and is thus reducing it. Finally, I will say that now I can just replace this whole dielectric by nothing but two surfaces, because ultimately it's only these two surfaces which have the induced charge. So instead of the whole dielectric, I can just take a look at these two surfaces and I will say that the polarized dielectric is equivalent or the same as two charged surfaces whose induced surface charge densities we will call as sigma p and minus sigma p. So of course minus sigma p represents the charge density of the negative charges and plus sigma p represents the charge density of the positive charges, and we know that the induced field opposes the external field. Once you have this, we can write down that the total field of the dielectric, inside the dielectric the total field will be reduced by these polarized dielectrics. So I can say that E dash, which is the total field inside the dielectric, is equal to the external field minus the induced field, right? We have said the induced field will reduce the external field. Now I can finally find out what is the actual polarization that is taking place. I want a formula for the polarization of the dielectric. So I say that let plus minus Qi be the induced surface charges, where obviously the plus Qi will be the induced positive charge and the minus Qi will be the induced negative charge. Okay, so we say that plus minus Qi are the induced surface charges and plus minus sigma p, as I have said, are the induced surface density of the charges. Note that the length of the slab is x and the area of cross section of the slab is equal to A. Now I will just simply apply the definition of the polarization. Polarization is dipole moment per unit volume. So first I have to find out what is dipole moment. Dipole moment is nothing but the charge into the separation. So here you have Qi into the separation, which is x, and the volume of the slab is simply given by the area into the length. So that will be A into x. And now polarization by definition is dipole moment upon volume, and therefore I will get P is equal to Q1x upon AX. And XX cancels and this will give me that P, that is the polarization, is equal to Qi by A. But Qi by A is nothing but charge per unit area and therefore by definition it is the charge density. And therefore we say that for linear isotropic dielectrics, the polarization is numerically equal to the surface charge density. that is the density of the induced surface charges, that is sigma p or minus sigma p. The magnitude of this will give us the numerical value of the polarization. Let's now see a small demonstration to understand the principle of capacitance. We know that the primary function of a capacitor is to store charge. Let us see how we can store charge in a conductor. Let's say I have a conductor. In this case, it is a metal plate. This metal plate in general will have equal number of positive and negative charges, and hence in general it will be neutral. In order to add charge to the metal plate, we use a battery which will provide a voltage. This voltage will try to force extra or additional charge into the plate. Initially, it will be very easy to add charge to the plate because the plate is uncharged. The green arrow represents the force of the voltage required to push additional charge into this plate. As more and more electrons are added to this plate, the force of repulsion faced by the incoming electron goes on increasing. Eventually, the repulsive force of the additional electrons on the plate and the force of the voltage trying to push the electron inside become equal, and no new charge can be added to the plate. If you try to push more and more charge into the plate, the charge starts to leak. In order to increase the capacity of storage of the plate, we bring another plate close to the first one. Plate 2 is neutral, whereas plate 1 is negatively charged as before. Because of the excess negative charge on plate 1, the electrons of plate 2 are repelled and move away from the plate. Plate 2 now becomes positively charged. The positive charge on plate 2 then attracts the negative charge on plate 1. Because of this attraction, the repulsive force of the electrons on plate 1 towards a new incoming electron is now reduced. This allows us to add more electrons to plate 1, and thus the capacity of storage of plate 1 has increased. Let's say now that plate 1 is given a positive charge. Due to this extra positive charge, if another plate is placed close to this plate, all the electrons on plate 2 will be attracted to the nearer surface of plate 1, and therefore one surface, that is the lower surface of plate 2, will have a negative charge. Consequently, the further surface of plate 2, that is the surface away from plate 1, will have a positive charge due to the lack of electrons. The negative charge on plate 2 reduces the potential on plate 1. At the same time, the positive charge on plate 2 will try to increase the potential on plate 1. However, the effect of the closer side of plate 2 is obviously more due to the lesser distance. Thus, overall, the potential of plate 1 is reduced. This means more charge can now be stored on plate 1. Hence, we see that just as before, bringing another plate close to plate 1 has increased its capacity to store charge. However, if we earth the outer side of the second plate, the positive charge on this side goes to earth. This increases the potential of plate 1 and results in plate 1 being able to hold even more charge. This is the principle of a capacitor. Let's now take a look at the principle of a capacitor. A capacitor consists of two conductors separated by an insulating medium. In fact, this arrangement of two conductors separated by an insulating medium is what we call as a capacitor. So why do we need the insulating medium? The insulating medium is necessary so that there is no conduction path between the two plates, that is the two conductors. So to ensure that there is no conduction path, we put an insulating medium between the two conductors. Now what we do is connect this to the terminals of a battery. And why do we do this? We know that the primary function of a capacitor is to store charge. And if it has to store charge, then the charge has to come from somewhere. So to supply this charge that we want to store inside the capacitor, we connect these conductors or plates, that is metal plates, to the terminals of a battery. Now it is obvious that when we connect the terminals of the battery to the plates, we know that plate A will lose electrons and therefore it will obtain a positive charge. So slowly the electrons of plate A will get attracted to the positive terminal of the battery, and this will leave a positive charge on plate A because all the electrons have gone away from the plate A. Now because the plate A has a positive charge, all the electrons on plate B will now be attracted towards plate A, and therefore the electrons from the battery also will start moving towards plate B because they are now ultimately attracted by the induced positive charge on plate A. So basically what is happening is that the electrons are going from plate A into the positive terminal of the battery, and the electrons are going from the negative terminal of the battery to the plate B. And therefore I can say that actually overall the situation is such that the electron is going from plate A to plate B. So overall I can say that there is an induced positive charge which is created on plate A, and there is an induced negative charge which is created on plate B. So what is happening here is this. So as you can see, an induced positive charge is created on plate A and an induced negative charge is created on plate B, and we will see that the exact amount of charge in magnitude will be induced on both the plates. So if plus 8 coulombs are induced on the positive plate, then minus 8 coulombs will be induced on the negative plate. The magnitude of the charge will be the same because whatever is leaving from plate A is going to plate B, and therefore the number or the magnitude of the charge will remain exactly the same for both of them. Also, the same amount of charge will be stored in both these plates irrespective of their shape. So both the conductors will save an equal amount of charge, that is store an equal amount of charge, even if it was some other shape, like for example if it was oval, if it was rectangular, if it was any shape, they would have an equal amount of charge stored in them. Okay, so this means that actually electrons are flowing from plate A to the battery and to plate B. But till when will this happen and when will it stop? Let's analyze the situation a little bit. When an electron leaves plate A, it is actually attracted by two different forces. The first one is the force of the plate on the electron, and the second one is the force of the battery on the electron. So let's say that the first force is Fp, that is plate on electron, and the second one is Fb, that is battery on electron. So now I want to ask you the question, initially just right at the beginning when the plates don't have any charge and the first charge, that is the first electron, comes out of the plate A, what exactly will happen is that it will definitely be attracted only to the battery because the plate is not exerting any force on the electron, and therefore initially all the force applied on the electron will be due to the battery. But however, once this electron goes into the battery, there will be a positive charge induced on plate A. And now because of this positive charge, what will happen is that the next electron that is trying to come out will experience some attractive force due to the positive charge on plate A. And therefore this next electron will have some force Fp attracting it towards the plate and the force Fb attracting it towards the battery, and as you can see the force of the battery is still greater and therefore it will go into the battery. However, eventually more and more electrons will leave plate A and the force of attraction towards the electron of the positive induced charge on the plate A will become equal to the force of attraction of the battery towards the electron, and therefore there will come a point where the electron will be equally attracted to the plate, that is Fp will be equal to the force of the battery, and therefore the electron will be equally attracted to the battery as well, and therefore I will say that Fp and Fb become equal. And at this point where the electron cannot decide should I go towards the positively charged plate or should I go towards the positively charged terminal of the battery, at this point the flow will stop. And now when this flow stops, even if you remove the battery and you remove the wires, this charge will still remain on the plates, that is still remain on the conductors, because there's no conduction path between them, and therefore you have successfully managed to store the charge on to the conductors. So therefore, this tells you what is the importance of the insulating medium. This is to make sure that the charge does not flow between the conductors even after I remove the battery and the wires. So this explains the importance of the insulating medium. Now obviously, if the two plates were not separated by an insulating medium, that is, if I connected them by a conducting path or a conducting medium, the charges from one plate would simply flow to the other plate and neutralize the charge on both the places, and the storage of the charge will definitely be lost. And this is how a capacitor actually works. Finally, I want to give you the formula for capacitance, that is C is equal to Q by V, where Q is the magnitude of charge on either of the conductors and V is the potential difference or the voltage between the plates. I also want to say that the charging of a capacitor takes place up to the same potential difference as is of the battery. So if you charge a capacitor with a 5-volt battery, then the voltage between the plates will be reached up to 5 volts. That's still when the charger will keep charging. Finally, remember that the capacitance of any capacitor depends on two things. First one is the geometry of the conductors, that is how wide they are, what is their area of cross section, how far away they are, and second is the nature of the medium between the two conductors, and therefore this medium in between will also change capacitance. The most common type of capacitors are the parallel plate capacitors. In such a capacitor, the two conductors are nothing but metal plates, and therefore we say that if the conductors are plane, the capacitor is known as a parallel plate capacitor. Now let's assume that the area of the plates is A and the distance between them is said to be D. Now in such a case, I will say that one of the plates has a positive charge and the other plate has the negative charge, and the plate with the positive charge we say has a charge density of plus sigma, and the plate with the negative charge has a charge density of minus sigma. Now we can know from the definition of charge density that sigma is equal to Q by A. We can use this for the magnitude of the charge density on the positive or the negative plate, only the plus or minus sign will differ. So Q is the charge on any plate and A is the area of the plate. Now what I want to do is find out the capacitance of a parallel plate capacitor, and to do this I have to analyze the effect of the plates in three regions of the parallel plate capacitor. So region 1 is the region which lies to the left of the positive plate, region 2 is the region lying between the plates, and region 3 is the region lying to the right of the negative plate. So now slowly I will start analyzing what is the effect of the electric field due to these two plates in each of these regions. Let's take a look at region 1. I say that in region 1, the positive charge on the positive plate will obviously be affecting region 1, and therefore the electric field due to the positive plate is indicated by the red arrows. Now, but what is the formula for this? We will assume that the distance between the plates is much bigger than the area of the plates, and when you make such an assumption, you can use the formula from electrostatics. That is, I will assume that this plate, each of these plates, is an infinite plane carrying charge density equal to sigma, and therefore I will use the formula for the electric field due to an infinite plane. And when I use that formula, I know that this will be sigma upon 2 epsilon naught. So I use the formula from electrostatics for electric field due to an infinite plane, and therefore I say that the effect of the electric field generated in the region 1 due to the positive plate is sigma upon 2 epsilon naught. Similarly, in region 1, the electric field will also be generated due to the negative plate, right? So the negative plate electric field is also reaching region 1, but this time it will be in the opposite direction, because we know electric field lines on a negative charge are always towards the negative charge. And therefore, as you can see, the yellow arrows indicate the direction of the electric field in region 1 created by the negative plate. However, again, I will use the formula for the infinite plane taken from electrostatics, and I will write this time minus sigma upon 2 epsilon naught, where minus comes from the fact that they are in opposite directions, and therefore I get that the total field in region 1 is actually 0. Now let's analyze region 3. The same picture takes place in region 3, that is, the electric field due to the positive plate in region 3 will be directed outwards, that is the red arrows, and this will be equal to sigma upon 2 epsilon naught, and the electric field in region 3 due to the negative plate will be directed inwards, that is the yellow arrows, and this will also be sigma upon 2 epsilon naught, but they are in opposite directions and cancel each other out, and therefore the electric field in region 3 is also equal to 0. The final thing remaining to analyze is the region between the two plates. Between the two plates, we will see that the electric field due to the positive plate will be towards the right, and therefore I write down sigma upon 2 epsilon naught. But the electric field due to the negative plate will also be towards the right, and therefore this time I will write plus sigma upon 2 epsilon naught because they actually add up to each other. That is, they are not in the opposite direction, they are in the same direction, and therefore their magnitudes actually get added up, and we get that the total field between the plates will be equal to E is equal to sigma upon epsilon naught. Now once I found the total field E is equal to sigma upon epsilon naught, I can write that down as Q upon epsilon naught A by simply substituting sigma is equal to Q upon A. Now one thing that you must note is that the direction of the electric field between the plates is from the positive to the negative plate. However, this electric field is not always straight and parallel. In fact, at the edges, that is, when the plates have a finite area, the field is not uniform throughout but exhibits outward bending. That is, at the edges you will see that the electric field is bending, and this is known as the fringing of the field. However, we want the field to be uniform, and therefore when we are discussing this parallel plate capacitor in our chapter, we are actually looking only at the middle part of the field where you can see that the field is nice and uniform and straight, and therefore we are ignoring this outward bending when we are talking about the parallel plate capacitor. Now we know that for a uniform electric field, potential difference can be written as simply the product of the electric field into the distance between the plate. So I say that the potential difference between the plates V can be written as ED. Now we also know that E we just found was Q upon epsilon naught A, and therefore I get that V is equal to Q upon epsilon naught A into D, and then we know that capacitance by definition is Q by V. Substituting the value of V from the formula above, we see that Q upon V, which is equal to epsilon naught A by D, and this gives us the formula for the capacitance of a parallel plate capacitor, that is C is equal to epsilon naught A by D. Now keep in mind one very important thing. We have found this capacitance for a parallel plate capacitor by assuming that there is no medium between the plates. This is for a case where the portion between the plates is a vacuum, and that's exactly why I have taken epsilon naught, because that is the permittivity of free space. We will shortly learn the effect of the dielectric in between the plates, but for now this formula is for when there is no medium between the plates. Once we have this formula, it is very easy to see what the capacitance of a parallel plate capacitor depends upon. The capacitance of a parallel plate capacitor is directly proportional to the area between the plates and inversely proportional to the distance between them. And therefore, this comes from the formula that we have found. Finally, I want to say that when fully charged, the voltage across the capacitor plates has the same voltage as the battery. And this completes the discussion on the parallel plate capacitor. We can also write down the formulae for the spherical and cylindrical capacitors with the same kind of arguments. In case of a spherical capacitor, the capacitor will be made up of two conductors, but both of them will be spherical. And in this case, the inner sphere will have a radius r1 and the outer sphere has a radius r2. And we can see that the inner sphere has a charge on it, but the outer sphere is earthed or connected to the ground. This is a spherical capacitor, and the formula for it is given by 4 pi k epsilon naught into r1 r2 upon r2 minus r1. Now similarly, a cylindrical capacitor is also made up of two conductors both having cylindrical shapes. The inner conductor, as you can see, is charged, whereas the outer one is connected to the ground again. The inner radius is r1 and the outer radius is r2, and the length of the cylinder is L, and we see that the capacitance in this case is 2 pi k epsilon naught L upon 2.303 log r2 by r1, and this is the formula for a cylindrical capacitor. So now what would happen if I fill the gap between the plates with a dielectric? So what we're trying to find out is what is the effect of the dielectric on the capacitance, and how will that initial formula change? We already know that in the absence of any dielectric, that is when there's vacuum between the plates, we found out that the electric field is sigma upon epsilon naught. Now I'm trying to find out what will happen if I place a dielectric in between. I already know that if I place a dielectric in between, we learned in the beginning of this video that this dielectric will be polarized. And when this dielectric is polarized, I can assume it to be exactly equal to two surfaces of charge density of sigma p and minus sigma p. So here I'm going to see something really important. I know that the plates of the capacitor have some charge density, that is plus sigma and minus sigma. And now, because of the electric field, the dielectric is polarized, and at the surfaces of this dielectric that is normal to the field, I have induced charge densities plus sigma p and minus sigma p. And you can see that these charge densities are opposite to the charge density on the plates. So this is obvious because the positive plate, which had a charge plus q, has some portion of it neutralized by the negative charge which is close to it. You see, the negative induced charge minus sigma p is lying close to the positive charge on the plate. So therefore, the total net charge that we can assume for the positive plate is reduced, and we say that the net charge is sigma minus sigma p on the positive plate. Similarly, for the negative plate, you can see that the induced positive charge is close to the negative plate, and therefore the net charge on the negative plate is also reduced in magnitude, and therefore I say that the net charge on the negative plate is sigma minus sigma p in magnitude as well. Now finally, I will say then that the electric field in the dielectric corresponds to the case when the net surface charge density on the plates is plus minus sigma p. So we say this is the net charge. And we also know that because of these induced charges on the dielectric surfaces, because of this there is a electric field, induced electric field, which is opposite to the external electric field due to the plates of the capacitor. And because of this, the total electric field inside the dielectric is reduced. So you can see this, that the number of lines inside the dielectric have been reduced because of the dielectric polarization. Also, this amount of reduction, we know that when a dielectric is introduced, the electric field inside it gets reduced, but how much will it get reduced depends upon the type of dielectric. If I switch this dielectric for another one, there will still be a reduction in the electric field, but it will be a different amount depending on that dielectric. And therefore, this reduction depends on which dielectric you are using. So overall, I want to say that the electric field in the dielectric reduces when it is placed in an external field. Now what happens? We say that when the dielectric is inserted fully between the plates of a capacitor, that is, if I insert a dielectric in such a way that it covers the entire area from plate to plate between the capacitor, in such a case I can write down the value for the potential difference between the plates in terms of this dielectric as follows. We already know that V is equal to ED in case of a uniform electric field, but now I will write down E as the net charge divided by epsilon naught into D, and the net charge now is sigma minus sigma p and not sigma like it was in the case for the vacuum. Now I have a dielectric in between, and therefore instead of sigma I have to write sigma minus sigma p, because we know that's the net charge, divided by epsilon naught and multiplied by D, which is the distance between the plates. So this is my new potential difference, that is sigma minus sigma p upon epsilon naught into D. From this now I can find the new formula for the capacitance. Now for the case of the linear isotropic dielectrics, which are the kinds that we are studying in this chapter, we assume that sigma minus sigma p is directly proportional to sigma. This is an assumption only valid for linear dielectrics. In this case, I will remove the proportionality sign and replace it with the constant 1 by k. And therefore I will get that sigma minus sigma p is equal to sigma by k. This is equation 2. This constant k is a characteristic of the dielectric. And now I will substitute the equation 2 in equation 1 and get that V is equal to sigma d upon k epsilon naught. Using this now I can find the capacitance of the capacitor with the dielectric, which I know is given by C is equal to Q by V, but V now is nothing but sigma d by k epsilon naught. So I substitute that in this formula for capacitance and I get the final answer for capacitance, that is C is equal to epsilon naught k q by sigma d. But I can simplify this further. I will replace sigma, which is the surface charge density, by q by a, and I get that C is equal to epsilon naught k q upon q by a into d. The q cancels and I get my final capacitance, that is C is equal to epsilon naught k a by d. Now remember, what is exactly this conclusion telling us? When there was no dielectric in between the plates, the capacitance was epsilon naught a by d. Now when there is a dielectric between the plates but from end to end, we see that the capacitance is epsilon naught ka by d. So the new capacitance is k times the old capacitance, and k is greater than 1, and therefore you can see that capacitance has actually increased by adding the dielectric between the two plates of the medium. So finally I can say that this equation has a constant called as epsilon naught k. This epsilon naught K together is the new epsilon, which is the permittivity of the medium. Initially, we had written epsilon naught, which was the permittivity of free space. When you put a dielectric, you can write it as epsilon, which is the permittivity of the medium, which is nothing but epsilon naught into K. And K is a characteristic of the medium. So from this, I can also see that if K is equal to 1, that means epsilon is equal to epsilon naught. And therefore, now we will define the general constant of permittivity, that is epsilon. And if you want to write down the permittivity for free space, you'll just say that epsilon is equal to epsilon naught into K, but K is 1. And therefore, for vacuum, epsilon is equal to epsilon naught. The dimensionless ratio, that is K is equal to epsilon upon epsilon naught, is known as the dielectric constant of the substance. And from here, I can see that K is the ratio of the new capacitance to the old capacitance. That is, it is the ratio of the capacitance after the dielectric was inserted upon the capacitance when there was only vacuum between the plates. And because K is greater than 1, I can say the dielectric constant is a factor by which the capacitance of a capacitor increases when a dielectric is inserted between the plates from end to end. That is, when a dielectric is fully inserted between the plates. Finally, I want to say that even though I found the value of this for a parallel plate capacitor, it is actually true for any type or any shape of any capacitor. So now let's write down the capacitance of a parallel plate capacitor in various cases. The first case we already know is the case when there is no dielectric between the two plates, that is when it is filled with vacuum or free space. So in case of this situation where there is no dielectric, we know that the capacitance is given by epsilon naught into A, where A is the area of the plates, divided by D, where D is the distance between the plates. So this is the formula for the capacitance for a parallel plate capacitor when there is no dielectric between the plates. The next we have the formula that we have just derived, that is the formula for capacitance when a dielectric completely fills the separation between the plates. In such a case, C is equal to epsilon naught Ka by D, where K is the dielectric constant of the material that you have placed between the plates. And we know that K is greater than 1, which means the capacitance has now increased. In fact, that is the definition of a dielectric. From here, we can also move on to the next case. Now, you can also have the capacitor being filled by a dielectric, but not completely. As you can see in this case, the dielectric is present only in some portion between the plates, and there is some portion between the plates which there is no dielectric. So if we write down the electric field inside the dielectric, we can use the formula that we know, that is E is equal to Q by K epsilon naught A. This formula can be used for the portion only where the dielectric is present. For the remaining portion, we cannot use this formula. So now if I try to write down the potential difference, that is V between the plates, then I will write down in terms of two regions. That is one region where the dielectric is present and the other region where the dielectric is not present. From this, I can write down the potential difference between the plates as V is equal to E naught. E naught is the field between the plates where the dielectric is not present, and therefore this portion will be D, which is the distance between the plates, minus T, which is the thickness of the dielectric. So this portion will have a potential difference of E naught into D minus T. Plus we write down the potential difference of the portion where the dielectric is present. In such a case, I will write it as E, where that is the electric field inside the dielectric, multiplied by T, because the dielectric is present only for the portion T. And therefore, now I will substitute E in this equation from the above equation, that is E is equal to Q upon K epsilon naught A. E naught we know is the electric field when no dielectric is present, and this will be nothing but Q upon epsilon naught A multiplied by D minus T, plus instead of E I will write Q by K epsilon naught A and multiply this by T, and this will give me the potential difference for between the plates. Now here you can see the quantity in the first bracket is the electric field when K is equal to 1, because this is for the portion where there is no dielectric, and the second portion in the bracket is the electric field in the medium with a dielectric constant equal to K. This gives me the total potential difference between the plates. Using this, I can find the capacitance of the plate simply by using the formula that C is equal to Q by V. Now here instead of V, I will replace the formula for V we have just found, and therefore I will get that C is equal to Q upon epsilon naught into A into the bracket D minus T plus T by K. Q cancels in the numerator and the denominator, and I get the final value of the capacitance, which is equal to epsilon naught A divided by D minus T plus T by K. Now looking at this equation, I want you to understand how to write this equation directly without solving it like the way we did right now. Simply speaking, the numerator remains the same whether there is a dielectric or whether there is no dielectric, but the denominator is made up of two portions. The first portion is the portion where you have free space, so that's D minus T. So that is the distance between the plates for which only free space is there, and the second portion T by K is for the portion where there is a dielectric. You write down the part of the distance between the plates where the dielectric is present, that is T, and you divide it by the dielectric constant, and you can do this in general. So D minus T represents the portion of free space and T by K represents the portion where dielectric is present. Now I can generalize this to a different case where instead of having only one dielectric, I have multiple dielectrics between the plates of different dielectric constants, for example K1, K2 and K3, and as you can see they are not even filling up the space between the plates. So now using the idea that I can write a general equation like I did in case 3, I will write epsilon naught A, that is the numerator as always is the same. In the denominator I have two parts. First I have to write down the part where I have only free space, and that will be nothing but D minus T1 plus T2 plus T3 all in a bracket. So you just add up the thicknesses of all the dielectrics, subtract that from the total distance between the plate, and that will give you the remaining portion where there is only free space. So this is the first part of the denominator. The second part will be T1 by K1 where the T1 is the thickness of the first dielectric, T2 by K2 where T2 is the thickness of the second dielectric, T3 by K3 and so on and so forth. So here you see we have a general formula for writing the capacitance between a parallel placed capacitor. Using this general formula we can tackle the last case, that is we want to find out the capacitance of a parallel plate capacitor when the medium between the plates is filled with a conducting medium. In such a case the dielectric constant comes out to be infinity, and the second portion, that is the T by K portion of the denominator, will simply become 0 because K is infinity, and the answer will come out to be C is equal to epsilon naught A divided by D minus T. Now just like resistors, capacitors can also be combined in a series or parallel combination. So let's first take a look at the combination of capacitors in a series combination. If I have two capacitors, say C1 and C2, and I connect them in a series combination, I can see very clearly that one end of the first capacitor is connected to the second end, and therefore this is the definition of a series combination. I can also see that the same current is flowing through both the capacitors. Eventually, after a period of time, both these capacitors will have the same charge on them. So let's say that the first plate, that is the plate on the left connected to the positive terminal of the battery, this plate of C1 will get a charge of plus Q, and the plate connected to the negative terminal of the battery, that is to the right plate of C2, will get a charge minus Q. Consequently, the charge on the second plate, that is the right plate of C1, will be minus Q, and the charge on the left plate of C2 will be Q. This is because the total charge on each capacitor must be equal to 0. Once we understand this, we have noted that the same charge is stored in each of the capacitors in a series combination. However, obviously there will be different voltages or potential difference between the ends of each of the capacitors. If V1 is the potential difference between the plate C1 and V2 is the potential difference between the plates of C2, then I know that the total potential will be V, which is equal to V1 plus V2. And for each of the capacitors, I can write down the capacitance formula, that is C is equal to Q by V, and from here I can get the value for V1, that will be Q upon C1, and V2, which will be Q upon C2, and I put that in this equation, so I get V is equal to Q upon C1 plus Q upon C2. I take the Q to the other side and I get V by Q is equal to 1 upon C1 plus 1 upon C2. Now what I do is write down the capacitance equation for the entire circuit. That is, I'm trying to find the effective capacitance. So suppose the total capacitance of the entire circuit is C. In such a case, I can write down the capacitance formula for the whole circuit, and therefore I can say that C for the whole circuit is equal to Q for the whole circuit divided by V for the whole circuit. And then using the comparison between the equations 1 and 2, what I get is the effective capacitance, that is, from 1 and 2, I get 1 upon Cs, which is my effective total capacitance, is equal to 1 upon C1 plus 1 upon C2. And this is how you get the effective capacitance in case of a series combination. What happens in case of a parallel combination? In case of the parallel combination, as you can see, the capacitors C1 and C2 are connected in a parallel combination, that is, both the plates are connected to each other. In such a case, the main difference between the series and parallel combination is that the charge stored in each of the capacitors will not be the same in a parallel combination. So let's say that the charge on the capacitor C1 is Q1 and the charge on the capacitor C2 is Q2. However, in this case, we can see that both the ends are connected to each other and therefore they will have the same potential difference V. Now, in this case, we will add up the charges. We will say that the total charge on the circuit is equal to the charge on the first capacitor plus the charge on the second capacitor. The charge on the first capacitor can be written as C1V from the capacitance equation, and the charge on the second capacitor, that is Q2, can be written as C2V, and then I say that the total charge of the entire circuit, that is the equivalent capacitor, will have a total charge of Q, which will be Q1 plus Q2. Now what I will do is write down the capacitance equation for the entire circuit as before, and that will be Q is equal to CV. But I can also say that Q is equal to Q1 plus Q2, and for Q1 and Q2 I will put the equations C1V plus C2V, that is Q is equal to C1V plus C2V. By comparing equations 1 and 2, I get C is equal to C1 plus C2. So in a parallel combination of capacitors, the capacitances just directly get added. You will note that the exact opposite treatment is required for resistors. For resistors in series combination, you directly add, and in parallel you add the reciprocals. In capacitors, in the series combination, you have to add the reciprocals, and in parallel you directly add the capacitances. You can also create a Wheatstone's bridge of capacitors, just like we did for resistances. So I want to look at the balance condition if I have a Wheatstone's bridge but made up of capacitors instead of resistances. So first let me tell you what is the balance condition. The balance condition means that the potential at point B and point D will be exactly the same, in which case there will be no flow of charge in the diagonal arm BD, and therefore this part, that is this arm, becomes ineffective, and so C5 becomes ineffective. So we will completely ignore this arm for the balanced condition. Now it's very simple to see that C1 and C2 are in series. You can see that they're connected on one side. So C1 and C2 are in series. Similarly, we will see that C3 and C4 are also in series. They are connected on one side. Now we can apply the formulae for the series capacitances. What we will first do is find out the potential difference between A and B, which will be VA minus VB, and as you can see, the only instrument in between where the potential will drop is the capacitance C1, for which we will write down Q upon C1. We need the voltage drop across the capacitor C1, and we know from the capacitance equation that V is equal to Q by C. So for the first capacitor, we'll write Q1 upon C1. So we got the potential difference between A and B, that is VA minus VB is equal to the voltage of the capacitor in between. We apply the same logic between VA and VD. But we know that this is the balance condition, so B and D are at the same potential, and therefore instead of writing VA minus VB, I can write it as VA minus VD. And if I try to write down the equation for VA minus VD, it should be equal to the voltage drop across the capacitor in between, which will be nothing but Q3 upon C3. Now we can do the same thing for the other side of the Wheatstone's bridge, that is I write VB minus VC is equal to the potential difference of the capacitor in between, which will be equal to Q2 upon C2. And again, VB has the same potential as VD, so instead of writing VB minus VC, I can write VD minus VC, and that will be nothing but the potential drop of the across the capacitance in between, that will be Q4 upon C4. From this I can get what I want, that is I want the balance condition. I take all these four equations and I will see very quickly that since VB is equal to VD, I get Q1 upon C1 is equal to Q3 upon C3, and Q2 upon C2 is equal to Q4 upon C4. So this is the balance condition if you have a Wheatstone's bridge made up of capacitors, that is Q1 upon C1 should be Q3 upon C3 and Q2 upon C2 should be Q4 upon C4. When this condition is satisfied, C5 can successfully be ignored. We know that capacitors are used to store energy. In fact, that's their primary function. We know this because when we connect the capacitor to a terminals of a battery, in such a case, the capacitor gets charged. And then this capacitor can be used as a source of charge for a short period of time. For example, we know that if I remove the battery in this case, the charge will still remain. And then I can use this capacitor, that is the charge on this capacitor, to actually flow current through the circuit, and I can actually light my bulb using the charge that was stored in the capacitor. So the work done by the battery in charging the capacitor gets stored inside the capacitor in the form of electric potential energy. And then when the capacitor is connected to some device, it uses this electric potential energy to flow current. So therefore we say that the capacitor stores some electric potential energy. Let's see what is the formula for this electric potential energy. Now, when the capacitor is charging, we are going to look at some intermediate time. That is, we are not looking at the beginning, we are looking at some random arbitrary moment in time where there is some charge on the capacitors, right? The capacitor charges from 0 to the final charge, that is plus Q. I am looking at the time period where I am somewhere in between, where the charge on the capacitor is plus Q dash and minus Q dash, that is on the plates of the capacitor. At this point, there will be some potential difference between the plates. Let's say that potential difference is V dash, and this V dash we can write down in terms of the charge at that moment in the capacitor. So we say that V dash is equal to Q dash by C. Notice that I have written C, I have not written C dash, because capacitance of a capacitor does not change. We know it's a constant. What is changing is the charge stored on the capacitor and the potential difference between the plates. So at this intermediate point, I know that V dash will be equal to Q dash by C. Now imagine that I have to transfer a small amount of charge, that is dq dash, from one end, that is from one plate, to the other. In such a case, I will find out what is the work done in transferring this small amount of charge, because finally when the entire capacitor is charged, this work done gets stored as electric potential energy, right? We said the work done by the battery gets stored as electric potential energy. So I'm asking, what is the work done by the battery to transfer this small dq dash amount of charge? We know that work done formula can be written in terms of the potential difference, and therefore I say that work done, which is dW, we are writing dW because it's only to transfer this small amount of charge dq. dW is nothing but V dash, which is the potential difference at that moment, into dq dash. So this is the work done for transferring this small amount of charge dq, and this work done is done by the battery, and this is stored as the electric potential energy. So we have dW is equal to V dash into dq dash. From here I can say that V dash, which we already know, is Q dash by C. So I bring that down and I say that dW is equal to Q dash by C into dq dash. I use this equation now to find the total work done. All I have to do is integrate this from the charge equal to 0 plus Q, and then I will get the total work done, and therefore I say that W is equal to the integration of dW from 0 to Q, because I am considering the work done when it was charging from charge Q is equal to 0 to charge Q is equal to Q, and therefore I see that W is equal to integration 0 to Q dW, and from here I will get this is equal to 0 to Q integration Q dash by C into dQ dash. But we know that C is a constant, so I take 1 by C outside, and I get this is equal to W is equal to 1 by C integration 0 to Q, Q dash dQ dash, and this is very simple, it's just like x dx. So this will give me an x square by 2, then I will put the limits from 0 to Q, and I get that W, which is nothing but the electrostatic potential energy, that is U, is equal to Q square upon 2C. And by using the capacitance formula that C is equal to QV, I can also write it in two other ways, that is half CV square, or I can write it as half into Q into V. So this gives me the formula for the energy stored inside a capacitor. Very early in the video, we learned that between the two capacitor plates lies the insulating medium, and the role of this insulating medium was to make sure that the charges don't go from one plate to another, that is from one conductor to another, because if they do, then the plates will get neutralized. And therefore, I want to talk about the idea of the common potential. Suppose I do have two conductors, and each of them have a capacitance of C1 and C2 respectively, and they are at voltages V1 and V2 which are not the same. Let's say V1 is greater than V2. First, I want to point out that here, even though we have a single conductor, we can still talk about its capacitance, because in this case, we will say that the conductor itself is one conductor and the earth is the second conductor. So each conductor itself can also have some capacitance if you assume that the second plate or the second conductor of that capacitance is the earth. So as you can see, each of them have been given a capacitance C1 and C2, and each of them have some voltage V1 and V2. Now I'm saying that V1 is greater than V2. This means that if I have a connecting wire between them, the charge will start flowing from C1 to C2 up to a point such that the potential between them becomes the same. And this same potential after the redistribution of charges is known as the common potential V. Now what I want to explain is what is changing or what is happening to the energy when it is flowing from one conductor to the other. So this common potential V, which will be the final potential of both the conductors, is given by C1V1 plus C2V2 upon C1 plus C2. And now I will look at the energy difference in the initial and final state of the conductors. We know that the potential energy formula is half CV square, and therefore in the initial state, that is when they are at different potentials, I can write down the potential energy of the first conductor as half C1V1 square and that of the second conductor as half C2V2 square. Now what happens after the conductors are connected with each other? The energy of the capacitors after connection can be given as half C1 plus C2 the whole into V square. Why? Because firstly these conductors are connected in parallel, because the earth is a common connection and the conductors are also being connected to each other. So this is a parallel connection. Their total capacitance will get straight up added, that is C1 plus C2, and the total potential difference is V, which is the common potential. From here I can find out what is the change in the potential energy, that is UF minus U1, and that will be equal to half C1 plus C2 the whole V square minus half C1 V1 square plus half C2 V2 square, and this will give me the final equation or expression for the change in potential energy, which is C1 C2 into V1 minus V2 the whole square divided by 2 C1 plus C2. So if you look at the numerator, we know that C, that is capacitance, can only be positive. So C1 C2 is a positive number and the other bracket, that is V1 minus V2, is squared. So the numerator is completely positive. Similarly, the denominator C1 C2 are again positive because capacitance is always positive, and therefore I see that delta U is positive. So this clearly shows that the energy is lost in the redistribution of these charges, and therefore because energy is lost, we ask the question, where did this energy go? And the answer is that this energy is manifested as heat when the charges flow through the connecting wire. So the heat that we feel in the connecting wire is actually nothing but the energy lost due to the redistribution of charges. One of the important applications of capacitors is that of the Van de Graaff generator. A Van de Graaff generator is a machine that can build voltages up to millions of volts, and these voltages then create large electric fields using which we can accelerate subatomic particles. Let's see what is the working principle of the Van de Graaff generator. Suppose we have a large spherical conducting shell on which we place a charge capital Q. The radius of the shell is capital R. Now we have seen in electrostatics that inside any conductor the potential is constant. Therefore, the potential inside the spherical shell will be constant and it is equal to the potential at its center, which is given by 1 upon 4 pi epsilon naught capital Q upon capital R. Now through some mechanism, if we are able to introduce a small sphere, another spherical conducting shell inside this bigger conducting shell having a radius of small r and placed on which is a charge of plus Q. Now again, we will analyze the potential due to this small sphere first. The potential due to this small sphere at any point outside the small sphere is equal to 1 upon 4 pi epsilon naught Q by R. Here we are looking at the potential due to the small sphere on any point on the bigger sphere. Since any point on the bigger sphere is outside the smaller sphere, we will use the formula 1 upon 4 pi epsilon naught Q by capital R, because capital R is the distance between any point on the larger sphere and the center of the smaller sphere. We can also write down the potential due to the smaller sphere at a point on the surface of the smaller sphere itself. In this case, the potential will be the same as the center potential of the smaller sphere. Here, the potential will be 1 upon 4 pi epsilon naught Q by small r, because small r is the distance between any point on the small sphere and its center. Using equations 1 and 2, we can now analyze the potential difference between any point on the smaller sphere and the larger sphere. Let's say we take a point A lying on the surface of the smaller sphere. Using the superposition principle, we can say that the potential at point A is nothing but the potential due to the larger sphere plus the potential due to the smaller sphere. Since point A lies inside the larger sphere, its potential will be the same as that on the surface and equal to 1 upon 4 pi epsilon naught capital Q by capital R. That is, we have to use equation 1. The potential due to the smaller sphere on point A is the same as its potential at its surface. Since point A lies on the surface of the smaller sphere, its potential is given by the second equation in equation 2. That is 1 upon 4 pi epsilon naught Q by R. Now we find the potential on a point lying on the larger or the outer sphere. Let B be a point on the outer sphere. The potential at B is equal to potential due to the outer sphere plus the potential due to the inner sphere. The potential due to the outer sphere is obtained from equation 1 and the potential due to the inner sphere is obtained from the first equation in equation 2. This is because for the smaller sphere, point B is a point on the surface of the outer shell, or we can say it is a point outside the shell. Thus now we have the potential at point A and the potential at point B. Now we can find the potential difference between these 2 points by simply subtracting B from A, that is VA minus VB is equal the potential due to A minus the potential due to V. The first terms in each of these brackets cancel on simplifying, and we get that the final potential difference expression is 1 upon 4 pi epsilon naught Q upon small r minus Q upon capital R. We can take Q out as common, and we will see that this means that delta V, which is the potential difference between the inner sphere and the outer sphere, is greater than 0. This is because capital R is greater in value than small r. It is important to notice that the potential difference between the inner and the outer sphere is independent of the charge on the outer sphere. No matter how big capital Q is, it does not factor into the equation for the potential difference. So finally, we have learned that the potential of the inner sphere is greater than the potential of the outer sphere, irrespective of how large capital Q is. And we know that charge flows from a higher potential to a lower potential. Therefore, if there is some way in which we could connect the sphere A with the sphere B, sphere A to sphere B, we'll see that charge starts flowing from sphere A onto the spherical shell B. Thus, we can keep adding the charge on the outer sphere no matter how large capital Q gets, because it does not appear in the equation for potential difference. Using this method, we can keep adding charge to the sphere A and it will keep getting transferred to the outer sphere. This charge will get accumulated to a large value, and this will serve the purpose of the Van de Graaff generator. So this completes all the concepts that we want to discuss under the concept of capacitors. Thank you for watching. Thank you for watching this video, and if you like our channel, please subscribe by clicking on the button below, and if you'd like to get your very own target book, you can click on the button here. Thank you for watching and stay tuned for more updates.